After dinosaurs became extinct due to environmental changes caused by meteorite impacts at the end of the Cretaceous period of the Mesozoic era, the climate eased into the Tertiary period. However, from the late Miocene onwards, the temperature gradually decreased and glaciers began to appear. After the Paleocene, the temperatures dropped even more as the Quaternary started. As a result, Earth's glaciers have become more massive. These climate changes have had a significant impact on human evolution and development. But did scientists accurately measure the temperature up to several million years ago? This episode introduces the secrets of the paleothermometer discovered by scientists. Please stay tuned to the end. The key word to understanding planet Earth is find the seawater temperature. Some of you might think, unless we went back in time with a time machine, how could you measure the temperature of the seawater in the distant past? However, marine geologists devised a structure that measures the water temperature by analyzing sediments containing past water temperature information. The secret to these sediments is related to the White Cliffs of Dover. The White Cliffs of Dover is a region in the English coastline facing the Strait of Dover in France. The cliff face, which reaches 110 meters, owes its striking appearance to composition of chalk accented by streaks of black flint, deposited during the late Cretaceous. The cliffs on both sides of the town in Dover in Kent stretches for 13 kilometers. Between 166 million years ago, Great Britain and much of Europe were submerged under a great sea during the late Cretaceous. The sea bottom was covered with white mud, formed from fragments of coccoliths, the skeletons of tiny algae that floated in the surface water and sank to the bottom, and together with the remains of bottom-living creatures formed muddy sediments. It is thought that the sediments were deposited very slowly, probably half a millimeter every year, equivalent to up to 180 coccoliths piled on top of one another. Up to 500 meters of sediments were deposited in some areas. The weight of overlying sediments caused the deposits to become consolidated into chalk. Then, due to the alpine orogeny, a major mountain-building event during the Cenozoic, the seafloor deposits were raised above sea level. The paleothermometer's secret lies in the coccolith, the sediments that make up the White Cliffs of Dover. The average depth of the world's ocean is about 3,800 meters. The deepest sea is located 15,000 kilometers east of the Philippines. It is the Challenger Deep in the Mariana Trench. The water depth of this sea is 11,000 meters, and even after Mount Everest is fully submerged, about 2,000 meters of water remains. But how deep can the sun's rays reach? This is less than 200 meters. Sunlight entering the sea is scattered or absorbed and does not reach deeper. In other words, the depth at which light goes is less than 5% of the ocean's surface layer. About 95% or more below that is truly a world of darkness. Microscopic floating organisms called phytoplankton live by converting a small amount of light obtained from the sun into energy. In addition, there are countless living organisms, such as zooplankton that eats them, fish that eats zooplankton, and bacteria that feed on the excrement and remains of plankton. Many of these plankton make beautiful crystals from silicon dioxide or calcium carbonate. The lifespan of each plankton is short enough to be insignificant, ranging from a few days to several months. It has a life cycle that ends immediately when it reproduces. They have been repeating such a lifestyle for hundreds of millions of years. The remains of the dead plankton slowly sink to the sea floor due to gravity. If you install a video camera in the deep sea and look at the surroundings with a searchlight, the deep ocean will always be like snowy weather, the remains of the plankton sinking into the sea. This is called marine snow. Shining brightly, the marine snow does not slowly fall into the sea thousands of meters deep for a long time. Among these sunken plankton is a paleothermometer that can measure ocean temperatures millions of years ago. This is the coccolith, an individual plate or scale of calcium carbonate formed by coccolithophores. Marine snow like this is thickly piled up on the seabed in the distant sea, more than 1,000 kilometers from the land. The average depth at which marine snow accumulates over a year is only a few tens of micrometers. In other words, only a few centimeters piled up around the 3rd century BC. However, on the seabed, the remains of this plankton sit down for a long time, become mud, and pile up in layers. Conversely, this means that the deeper you dig into the ground and the sea floor, the more likely you are to find the remains of plankton accumulated long ago. Imagine, for example, a layer of mud 1 kilometer thick at the bottom of the sea. If so, it is like the remains of the past 50 million years piled up one after another. In other words, it means that the history of the sea over 50 million years is preserved in the mud. When examining the seabed, there's a layer of mud more than 1 kilometer thick. Therefore, the history of the sea recorded by the mud may exceed 100 million years. Then how can we scoop out the mud piled up on thousands of meters of the sea floor? First, geologists pierce the seafloor with long metal tubes suspended from the top of weights that look sloppy, but weigh hundreds of kilograms. It's a clunky tool called a corer. Geologists have used this tool to collect mud from the seabed. On the ship, a large balcony with a corer on one side and a trigger on the other is sent down to the sea floor using a wire. When the trigger, located slightly lower than the tip of the corer, falls to the sea floor, the scale loses balance, and the meshing metal is released, causing the corer to fall by gravity and land on the sea floor. When it is pulled up, the negative pressure is applied by the piston installed in the tube to prevent the collected sediments from falling. How did scientists know about the temperature of the seawater millions of years ago from coccoliths taken from the bottom of the sea? The temperature of the seawater is an important criterion, especially the surface water temperature of the ocean at a depth of 100 meters where many organisms live. Cesare Emiliani was the first quantitative measure of past climate change based on this scale. In 1945, when World War II had just ended, a young man received a doctorate from the University of Bologna, Italy, studying foraminifera, zooplankton. He applied for a program supported by the victorious United States and received a scholarship and another PhD in geology and foraminifera research from the University of Chicago. After graduating, he was hired as a research fellow by Professor Harold Urey at the University of Chicago's Institute for Nuclear Studies. Harold Urey, director of the Research Institute, was a famous professor who received the Nobel Prize in Chemistry for discovering heavy hydrogen atoms called heavy water reactors at the time. The research topic Emiliani was given in Urey's laboratory was a detailed analysis of the oxygen isotope ratio of calcium carbonate shells made by foraminifera in seabed sediments. Urey was invited to lecture at the Swiss Federal Institute of Technology in Zurich. In that lecture, he explained how the isotopic composition of the oxygen atom changes between the evaporating water vapor and the original water. He then predicted that seawater would have a slightly higher oxygen isotope rate than freshwater. A well-known mineralogist, Paul Niggli, who listened to the lecture, suggested, "Isn't the oxygen isotope ratio recorded in marble made of calcium carbonate produced from seawater?" Nigli's opinion sparked Urey's return to Chicago, and he immediately began calculating the oxygen isotope ratio relationship. And he realized that the oxygen isotope ratio of calcium carbonate could pinpoint the water from which it originated and the temperature at which it precipitated. "I realized at that moment I had a paleothermometer in my hand," Urey recalled. So he decided to use the paleothermometer to apply it to climate change at the boundary between the Cretaceous period and the Tertiary period, when dinosaurs were extinct. At that time, a graduate student at the lab proposes to find out the climate change of the Ice Age by measuring the oxygen isotope ratio for foraminifera shells and sediments. Urey immediately recruited Emiliani, who had just received his second PhD from the University of Chicago on foraminifera research. Here, let's go over how the oxygen isotope ratio of calcium carbonate can be a paleothermometer. To do so, looking at the oxygen atoms in the water is necessary. The water molecule is represented by the chemical formula H2O, consisting of 2 hydrogen atoms and 1 oxygen atom. First, let's pay attention to the oxygen atom. Most oxygen atoms in nature comprise 8 proteins, 8 neutrons, and 8 electrons. The mass number of an oxygen atom is 16, the sum of the number of protons and neutrons. However, oxygen-17 and oxygen-18, which have 1 more neutron, exist in nature, albeit in tiny amounts. In other words, oxygen-18 is slightly heavier than oxygen atoms. Currently, seawater contains oxygen-18 at a meager rate of 0.2%. This means that there is 1 oxygen-18 in 500 water molecules. The shells of foraminifera living in the ocean surface water are made of calcium carbonate, which combines calcium ions dissolved in seawater with carbonate ions. One molecule of calcium carbonate contains 3 oxygen atoms. What Emiliani analyzed was the concentration of oxygen-18 in this oxygen. In seawater, carbon dioxide reacts with water to form carbonic acid. Carbon dioxide is a gas that dissolves in water, and 1.4 liters of carbon dioxide dissolves in 1 liter of salt water at 1 atmospheric pressure and 0 degrees Celsius. Carbon dioxide dissolved in water is converted into carbonic acid by carbonate ions and carbonic acid ions, which is consistently repeated. During this changing process, oxygen-16 and oxygen-18 show slightly different states. For example, the concentration of oxygen-18 in carbonate ions is 1.4 times higher than the concentration of oxygen-18 in water. Emiliani knows that Foraminifera is an organism that absorbs carbonate ions from seawater and makes a calcium carbonate shell. In water at 25 degrees Celsius, the concentration of oxygen-18 in calcium carbonate is 2.9% higher than the concentration of oxygen-18 in water. Urey established a theory about concentration of oxygen isotopes in water and carbon dioxide and verified it using reared claims. As a result of the verification, when the water temperature rises by 4 degrees, the oxygen isotope ratio of calcium carbonate decreases by 1%. The error was only plus over minus 0.1 per mil. It was amazingly precise. Let's get back to Emiliani's story. Emiliani analyzed the oxygen isotope ratio of foraminifera contained in the seabed core of the Caribbean Sea and published it in a Journal of Geology in 1955. The cooling corresponding to the Ice Age occurred relatively slowly, and it was a general pattern that the coldest period came in the second half of the Ice Age, which lasted for tens of thousands of years. And the warming progresses from glacial to interglacial occurs in a relatively short period of about 10,000 years. Therefore, climate change has happened in a sawtooth pattern, not a sinusoid. It can be seen that the difference in oxygen isotopes between glacial and interglacial period is about 2 per mil. This result is quite important. This is because, according to the calculations of the paleothermometer, the water temperature was 8 degrees Celsius cooler than it is now during the Ice Age. Emiliani analyzed oxygen isotopes of seabed cores collected from 10 locations, including the Atlantic and Pacific Oceans, to confirm this result. And he confirmed that all seafloor cores recorded oxygen isotope changes similar to those in the Caribbean. This result suggested that climate change has occurred on a global scale. Emiliani labeled the current interglacial as Stage 1, the preceding interglacial as Stage 2, and the preceding interglacial as Stage 3. Interglacials are given odd stage numbers, as colder ice ages are even numbered. It is also called MIS-1 or Marine Isotope Stage 1, MIS-2, and etc. Initially, Emiliani did not consider that the oxygen isotope composition of seawater changes due to convection and condensation of water vapor. Seawater, passing through the tropics, evaporates. As explained above, among the isotopes of O are light isotope oxygen-16 and the heavy isotope oxygen-18. Which of these will evaporate first? Naturally, water containing the light isotope oxygen-16 or H2O will evaporate first. So, the proportion of oxygen-18 in freshly evaporated water is about 10 per mil lower. And if the water vapor containing oxygen-16 turns into rain and falls into the sea, the oxygen-18 concentration in the sea will not change. Now suppose that an air mass with plenty of moisture from the warm sea of the tropics moves to the interior of the continent at high latitudes by atmospheric circulation. Then, the water vapor containing heavy oxygen-18 will fall as rain or snow, so the composition of oxygen-18 will decrease as you go inland. As a practical example, the oxygen isotope ratio of snow falling in central Greenland is 30 per mil. This change will not change the oxygen isotope ratio of seawater because rainwater quickly returns to the sea through rivers. However, if this evaporated water does not flow into the sea, becomes a continental glacier, and stays on land for a long time, the story is different. During the Ice Age, large amounts of water lacking heavy water molecules became massive continental glaciers anchored in North America and Europe. This means that the Ice Age oceans were rich in water containing more oxygen-18, a heavier water molecule. In this case, the oxygen isotope ratio curve announced by Emiliani is converted to paleo template as it is. The water temperature will be misread as much as the oxygen isotope change in seawater. Based on this circumstantial evidence, Emiliani thought that the oxygen isotopes of Ice Age seawater contained water molecules that were 0.5 per mil heavier than seawater. Therefore, 0.5 mil was subtracted from the 2 per mil difference between the glacial and interglacial periods in the graph described above. Then, the remaining 1.5 per mil is due to the change in water temperature. This corresponds to the 6 degrees Celsius, so he concluded that the Ice Age surface water temperature in the Caribbean Sea was 6 degrees cooler than today. At the time, to measure oxygen isotopes with a mass spectrometer developed at the University of Chicago, as many as 400 foraminifera had to be collected from the sediment. Finding and collecting 400 small foraminifera less than 1 millimeter in diameter through a microscope was more complicated than expected. Nicholas Shackleton of Cambridge University made a mass spectrometer capable of measuring the oxygen isotope ratio with the same precision with only 1/10 of the previous sample by weighing the existing machine. Varieties of foraminifera that live in the ocean's surface layer also live in the bottom of the sea, feeding on marine snow that falls to the dark seabed. Since they also make calcium carbonate shells, the oxygen isotope ratios in the shells would contain important information about the waters near the seabed. However, since the number of these benthic foraminifera shell fossils in seabed sediments is much smaller than that of planktonic foraminifera, the oxygen isotope ratio of benthic foraminifera, which had a small population at the time, could not be calculated using mass spectrometry. It was almost impossible to measure. It was Shackleton who made this possible. He succeeded in measuring the oxygen isotope ratio of benthic foramin collected from the Caribbean Sea with his improvised mass spectrometer. As a result, as shown in the screen, it was found that the oxygen isotope ratio of the benthic foraminifera shell changed by about 1.5 per mil, according to the climate change between the Ice Age and the interglacial period. So, how should we interpret these results? It can be said that the difference in the oxygen isotope ratio of benthic foraminifera found by Shackleton was caused by factors other than water temperature. During the Ice Age, continental glaciers with relatively few heavy water molecules were formed, and instead, heavy water molecules in seawater increased, increasing the oxygen isotope ratio by 1.5 per mil. This was much larger than the 0.5 per mil that Emiliani had thought. In other words, it means that 0.5 per mil minus 1.5 from 2.0 of the oxygen isotope ratio difference between the Ice Age and the interglacial period is due to the change in water temperature. In terms of water temperature, this is only 2 degrees Celsius. It can be seen that the paleo temperature has not changed as much as Emiliani thought. In this transition from Urey to Emiliani to Shackleton, most of the code for oxygen isotope ratios in foraminifera fossils have been solved. It became clear that records of oxygen isotope ratios inscribed in seafloor sediments, initially considered paleothermometers, were indicators that could be termed interchangeably continental glacier meters. The study of paleoclimate reconstructions, which until then often relied on the experience and predictions of geologists, has now opened up new avenues. Currently, sea cores are extracted from thousands of places under the sea and analyzed by scientists. As a result, it is possible to very accurately estimate the temperature of the Earth tens of millions of years ago. Therefore, the global temperature graph on the current screen is very reliable. Meanwhile, in the mid-1950s, when Emiliani was completing a revolutionary achievement using the oxygen isotope ratio of foraminifera at the University of Copenhagen, Denmark, collected rain and snow from all over the world to measure the oxygen isotope ratio there was. Dansgaard was interested in any relationship between daily weather conditions and oxygen isotope ratios. He analyzes Greenland ice cores. More details about this are introduced in the following video. Thank you for watching until the end. Please give a thumbs up, subscribe, and turn on notifications.